In previous class, we have solved numericals on the circle diagram of induction motor. Now again, we'll continue with the numericals. I'll read out the statement of the numerical. It's draw the circle diagram of a 7.46 kilowatt, 200 volt, 50 hertz, three-phase slip ring induction motor with a rotor connected stator and rotor. Slip ring induction motor with a star connected stator and rotor, a winding ratio of unity, a stator of 0.38 ohms per phase and a rotor resistance of 0.24 ohms per phase. I'll write down the given data here. It's a 7.46 kilowatt, 200 volts, 50 hertz, three-phase slip ring induction motor with star connected, winding ratio of K is 1, stator resistance R1 is equal to 0.38, R2 is equal to 0.24 ohms. This is also in ohms. Now they have given no load test results and block rotor test results. No load test results are 200 volts, 7.7 amperes, and cos phi naught is 0.195. Block rotor is 100 volts, 47.6 amperes, and cos phi s is 0.454. Now using this given data, we should start plotting the graph, and they have asked us to calculate first point, starting torque, second point, maximum torque, third point, maximum power factor, fourth point, slip for maximum torque, fifth point, maximum output. Now to calculate all these things, first we should be having the circle diagram. Now to draw this circle diagram, here I have no load test results as well as block rotor test results. This is V naught, I naught, and cos phi naught. Here we have, and here from the block rotor test results I have VSC, ISC, and cos phi SC. Now using this no load test results and block rotor test results, I should be calculating first ISN. First of all, phi naught, the angle phi naught. That is nothing but cos inverse of 0.195 will get us the phi naught. So I should be calculating phi SC, then ISN, then WSN. Okay, let's start with the solution. Now phi naught is cos inverse of 0.195. This results in 78.7 degrees. Similarly, phi SC is equal to cos inverse of 0.454. This results in 63 degrees. Once I have this, I can calculate next parameter, that is ISN. ISN is equal to now this is the equation. So here it is 100 over its 47.6 into 200. So this will result in 95.2. So this is about ISN. Now we can also calculate WSN. WSN here, since we do not require, just hold a second. Here I have the equation for the WSN, that WSN is equal to root 3 V naught ISC cos phi SC. If I do this, I'll be getting the answer as 14,970 watts. Okay. After having this WSN, now I can start drawing the circle diagram. Let the vertical axis be the voltage axis, V, and then let the horizontal axis be the current axis. Now, choosing the appropriate current scale, I can start drawing the graph. Now here ISN is 95.2 amperes. 95.2 amperes. So I should be accommodating this ISN in my graph page. As we already know, the length of the graph page will be hardly 20 to 30 centimeters. So fixing up this 95.2 amperes in the graph page should be done using the appropriate current scale. Current scale again will take it as 1 centimeter is equal to 5 amperes. This will make, approximately considering this as 100, the length of ISN will be around 20 centimeters, okay? Such that we should be selecting the current scale such that this should fix up, this can be drawn easily in the graph page, okay? Now 1 centimeter is equal to 5 amperes. That means this will get divided by 5. So hardly it will be around 19 to 20 centimeters, okay? And now this I naught is 7.7 amperes. So 7.7 divided by 5 will get us the length as 0. For time being, not 5, will make it as 10, okay? Okay? Any scale you people can refer, but here I'm going to take it as 10 because already I have solved it using the 10. So I'll make it 10. The current scale is 1 centimeter is equal to 10 amperes. If I do that, to make the calculation easy, I have done that. Now this will be current 7.7 amperes. I naught will be 0.7 centimeters. Now I should be drawing that 0.7 centimeter line at an angle of 78.7 degrees with the V, okay? So at an angle of 78.7 degrees, I should be drawing this I naught line, which is of 0.77 centimeters, and then name the line. The origin is named as O, and this is O dash. Now from the tip of this O dash, draw a horizontal line to the axis, okay? Now I should be drawing this ISN. ISN is 95.2 amperes. Now the current scale is again 1 centimeter is equal to 10 amperes. That means the length of ISN line will be 9.52 centimeters. Now I should be drawing this ISN in the graph page by making an angle of 63 degrees with the V. So taking 63 degrees from this side, at an angle of 63 degrees, I'm drawing this ISN for 9.5 centimeters. This is 9.5 centimeters, okay? Now this is ISN. This is ISN. Now from the tip of O dash, I should be connecting this to this point. I'm naming this point as point A. Now this is our output line. Now we should, as per the procedure, I should be bisecting this O dash A line. Bisecting the O dash A line, okay, and then extending the line till it reaches the horizontal axis, okay. Now mark this point as point C. I'll again explain how to bisect the line, okay. This O dash a line I should be bisecting. So keeping the compass more than half length, keeping the length of the compass more than half, I should be drawing the arcs, and then keeping the needle of the compass on this side, setting it for more than half, I should be drawing the arcs here, and then joining these corners and extending the line till the horizontal axis, I'll get this point C. Now, keeping the point C as the center and O dash C as the radius, draw a semicircle starting from O dash and then joining it back to the horizontal line and naming this point as point B. Okay, this is point C. Now, here from the point A, draw a vertical line downwards till it reaches the horizontal axis. Now, naming this point as point B and this point as F. Okay. Now, the thing is, I should be marking the point E on this line AF. I should be marking the point E on the line AF, which bifurcates the rotor copper loss and stator copper loss. Since we know that it's a slip ring induction motor, obviously the equation is rotor copper loss, the ratio of rotor copper loss to the stator copper loss is equal to R2 dash to R1. Okay, R2 dash to R1, and here they have given stator copper loss at rated voltage under blocked rotor condition. This can be taken as 3 times ISN squared into R1. This results in 3 times ISN we have calculated either we can go for this thing or directly we can go for R2 dash by R1, which is 0.24 divided by 0.38. Here the equation is like R2 dash is equal to R2 here because since the value of K is equal to 1, even R2 dash will also remain same. Okay, so this method is easy. Okay, and we will neglect this. Okay, here rotor copper loss, the ratio of rotor copper loss to stator copper loss can be given by R2 dash by R1. We have discussed this in the previous classes. Now R2 dash is also equal to R2 because the value of K is equal to 1. The ratio, the turns ratio is equal to 1, so R2 dash is equal to R2. So I have taken the same value of R2 to the R2 dash. Now 0.24 by 0.38, it results in, here I'm marking this, I'm taking this as AE divided by EF as 0.24 to 0.38. Okay, now this entire length AF is of length 0.62. Okay, wait a second. The length AF is 4.3 centimeters. Okay, now we'll convert this. Now we know that the power scale, we'll check out the power scale first. Power scale can be calculated using this WSN and the length of AF. Now this WSN is here. Okay, WSN is from A to D. Okay, and it is 14,970, and we also know the length of AF. Okay, sorry, this is length of AD. Okay, now power scale is 14,970 watts divided by 4.3 centimeters. This results in 3,481 watts per centimeter. Okay, power scale is 3,481 watts per centimeter. Now we can write AE divided by AF is equal to 0.24 divided by 0.62. Now AE is equal to AF into 0.24 divided by 0.62. This is equal to 4.1 into 0.24 divided by 0.62, which results in 1.6 centimeters. Now let me explain you this thing. Here we have calculated the power scale, and then we know that the ratio of AE to EF, AE to EF is in the ratio of 0.24 to 0.38 because it is R2 dash divided by R1 and R2 is also equal to 0.24. Now this is in the ratio of 0.24 to 0.38, and if I measure this AF, it is equal to 0.62, okay, or else obviously that should be equal to AE plus EF. If I add these two, I'll be getting 0.62. Okay. Now, if I consider the ratio of AE to AF, it will be in the ratio of 0.24 to 0.62 because AF is nothing but AE plus EF. So obviously AE is equal to AF. By shifting on to the right hand side, I'll be writing this as AF into 0.24 by 0.62. Now AF, the length of AF is in terms of centimeters, that is 4.1. Now 4.1 into this will get us this 1.6 centimeters. Now AE is equal to 1.6 centimeters. AE is equal to 1.6 centimeters, and this remaining will be 4.1 minus 1.6 centimeters. Now from this point A, measuring 1.6 centimeters downwards, I'll be getting the point E. Okay, here I have the point E. Now from the point O dash, I can join it to the point E, and I'll be calling this as torque line. This is the torque line. Okay. Now after this, I should be calculating the first point, that is starting torque. Starting torque is nothing but the length AE. We know the length AE, okay, which is equal to 1.6 centimeters, but I want AE in terms of synchronous watts. So starting torque can be given by 1.6 into the power scale, 3481. Okay, if I do this, I'll be getting this as 5570. You can keep the answer of the torque either in terms of synchronous watts or in terms of Newton meters. If you want to convert this into Newton meters, then obviously you should be using the formula P is equal to omega T, or torque is equal to P divided by omega. To this, if you divide it by the omega, which is equal to 2 pi ns divided by 60, we'll be getting this torque in terms of Newton meter. Okay, and then the second question they have asked us to calculate is maximum torque. Maximum torque. To calculate the maximum torque, I should be drawing a parallel line to this torque line, which should also be the tangent to the circle. So this is the line, this is the torque line. I'm going to draw a horizontal line, a parallel line, which is also a tangent to the circle at this point. So this is the maximum torque point. Now I should be drawing a line vertically downwards till it reaches the torque line, and I'm naming this point as point M and this point as point N. Okay, the length of Mn will give us the maximum torque. Length of Mn, if we measure, it will be around 3.57 centimeters. So the maximum torque Tmax will be into 3481, which is equal to 12,427 synchronous watts. Okay, again here this is also the torque which is in synchronous watts. Now again, to convert this into Newton meter, you can divide the answer by the omega. Omega is again 2 pi ns by 60. Now after this, the next point they have asked is slip for maximum torque. I'll erase it here. Slip for maximum torque, third point. Sorry, third point is maximum power factor. To get this maximum power factor, draw a line, draw a tangent to the circle from the point O. So if I write a tangent to the semicircle from the point O, which meets at point P, then this is the maximum power factor. Okay, then just draw a line vertically downwards till it reaches the horizontal axis. Now actually this angle gives us the power factor, the angle for the power factor, because this angle and this angle are same. So here, to get this, it's nothing but the equation cos phi is equal to base divided by hypotenuse. Okay, and here this is point P Px, I'll name it as. So here directly taking the ratio of Px to OP will get us the cos phi, and which is equal to 0.875 lagging. Okay, and next the fourth point is to calculate the slip for maximum torque. Slip for maximum torque. Now for the maximum torque, we have the equation. I'll name this point from the point where we had got the maximum torque. Okay, the line intersecting with the output line, I'll name this as point K. Okay, now slip can be given by the equation Kn divided by Mn. Now this results in 0.7 divided by 3.57, which is equal to 0.196, or else, yeah, this is slip for the maximum torque. Okay. Next, the fifth point they had asked was maximum output. Maximum output can be calculated by drawing a parallel line to this output line, which should also be the tangent to the circle. Now obviously, if I extend this line backwards, here at this point I'll be getting the maximum output line. Okay, now that point I'll name it as point L, MNL. Okay, L, and draw a vertically downward line till it reaches the output line. Okay, and I'll name this point as Y. Now measure the length Ly, measure the length Ly, length of Ly. It is 2.95 centimeters. 2.95 centimeters. And now maximum output in terms of watts can be given by 2.95 centimeters into, that is power scale 3481 watts per centimeter, and it results in 10,270 watts. 10,270 watts. Now here, since we have calculated the maximum output 10,270 watts, that too at this point, this is the maximum output. We will not get the output more than 10,270 watts. That is fixed. Okay, that is not possible. Okay, although the rating of the machine is 7.46 kilowatts, that means the actual running condition of the induction motor is 7.46 kilowatts, but under maximum loaded condition, the maximum output the motor can give is 10,270 watts. But we know that we cannot run the induction motor continuously under this maximum loading condition. Okay, the rated output of the machine is 7.46 kilowatts. So if sometimes by mistake if it exceeds, then also for some time it is okay. But the maximum output which the motor can give is 10,270 watts. Okay, here it completes. Here it gets over the numerical. All 5 points we have calculated.